back again to another video. In this video series, we are going to talk about the photochemistry, right? So this is our first video. In our first video, let's talk about the introduction to photochemistry. What is this photochemistry? Why do we need it? What's the importance of this, right? So let's consider a simple reaction, right? So let's take capital A. This is our reactants, which is going to be formed up to P, which is the products. No, so this is a normal reaction, and this is its energy diagram. So this is the reaction coordinates, and this is the energy. You know, here we have the reactants, here we have the products, and I hope you know what does this energy difference means. Let me put it like delta E1. So this is delta E1. This is the energy barrier, activation energy barrier. So this A molecule should surmount this energy barrier in order to proceed with the reaction. You know it, right? Now, what we do in photochemistry is we are going to give energy, right? We are going to give specific energy to this A reactants, and we are going to excite it. Now, we are going to excite these A molecules into a higher energy levels. Yeah. So this is the ground state. Now we have excited our A molecules, which is in excited state. We are going to talk more details about this excitation process, right? For now, just get the idea. We are going to excitation. Okay. Now our A molecules are in this place. We have excited it. Now look at this. The A molecules has to go through this particular reaction coordinate. Now the energy difference, I can denote it as delta E2. Okay, this is our new activational barrier. So you can see delta E2, which is our new activational barrier after the excitation, is less than delta E1. So this reaction through this excitation state, right? Reaction through this excitation is much more feasible because it has lower energy to surpass, right? So I hope you get the idea. So this is what we are doing in the photochemistry. We are going to excite our molecules, so the activation energy barrier would be lowered compared to our initial state, and then the reaction would be much more feasible than before. So this is the basic principle in our photochemistry. Now let's move on to this excitation process. What is this excitation means? How this excitation happens. Okay, now if we take a molecule, right, let's take, this is our molecule, this is a molecule. So molecule has various of energy levels. So here we have the first energy level, the ground state energy level, then these are here, right, energy levels. There are energy levels. I can denote it S0, S1, S2, S3, S4 up to infinity. There are energy levels. So there can be electronic transitions, right? Here a ground state can be excited up to S1, S2, S3. Likewise, we can denote this excitation. We can denote these transitions. Now in photochemistry, we are more focused on these two states, ground state and the first excited state, because now when it comes to the photochemical reactions, okay, when it comes to the photochemical reactions, here let me take this white color. When we have A molecules which is going to react to our products, these molecules should collide each other, right? Otherwise they have to be interacted each other in order to form the products. Now we know from our previous knowledge here, the excitation helps us to go through more feasibly, more easily through this activation barrier. So more excited you are, it's easier to surpass this energy barrier. But the thing is here, when a molecule excited into a high energy state, let's say our molecule has excited up to this energy state S3. Now this is much more higher energy state, right? So this is much more unstable. So what happens is, as soon as get it excited, it will come back to its ground state by releasing the energy. So the lifetime of these higher energy states, let's denote it as tau. This tau is much more lower because they are much more unstable. So this lifetime of these higher energy states are not enough to undergo this particular reaction. Only energy level which has sufficient lifetime to go through these reactions are the first excitation in this S1. So that's why we are going to forget about our higher energy levels, higher electronic transitions. We are going to forget these things. We are going to focus on this ground state and the first excited state, right? So now let's say we have our electron configuration like this to our molecule. Okay, so this is the place, this is the electron pair which is going to be excited. So there are two ways this can be excited. There are two ways to get this excited. One way is to like this. Okay, let me draw it. Yeah, one way like is like this. Here we have this electron like this. So this is the electron which has been excited. Okay, so I will denote it as 1 2 1 2, and the other way is like this. So this is 1 2. So you can see in our this particular orientation, right, the spin has changed, right? The spin has changed. In this case the spin has not been changed. You can see initial spin is the same after the excitation. If you remember your spectroscopic knowledge, right, in order to obtain a acceptable transition, the spin change must be 0. This is a condition. This is a selection rule. In our spectroscopy we have talked about this. So spin change must be 0. So we can say this is, look at this place, when we are going through, this is the ground state. Okay, when this is the after the excitation, this total spin, like the spin is not been changed, right? The same spin as here. Delta S is 0. So this is acceptable. Acceptable transition, otherwise allowed transition. But in this case you can see delta S is not 0. So we call this as forbidden transition. Forbidden transitions, right? Forbidden transitions. So let's also move into the multiplicity. So here the total spin, right, you can see this electron has positive 1/2 and this electron has negative 1/2. Total spin is 0. So what is the multiplicity? So if you remember the multiplicity, we calculate by 2s plus 1. S is the total spin. So total spin is 0. So multiplicity is 1. So this state, this ground state, okay, this is the ground state. This ground state is a singlet state. Singlet. This is a singlet state. Okay? This is a singlet state. So let's go to here, this excitation state. So here the total spin is same, the 0. That's why we have to mentioned it as acceptable transition or allowed transition, because the total spin is not changed. So it follows our selection rule. Okay. Now we have our total spin is 0. So multiplicity, just like here, is 1. So this is also a singlet state. So this is a singlet excited state. Okay, this is the singlet excited state. Now here, this guy, you can see the total spin, right, is, this is 1/2, this is 1/2, and 1/2 plus 1/2 is 1. Total spin is 1. So let's move on to the multiplicity. Multiplicity, 2s plus 1. Now s is 1. Okay, so multiplicity is 3. So this is a triplet excited state. This is also an excited state, right? This is a triplet excited state. So you can see now when the excitation happens, okay, from a singlet state to a singlet excited state, which is acceptable, which is allowed. But singlet ground state to a triplet excited state, right? It is not allowed. It's a forbidden transition in photochemistry. Okay, so this is the second main point, second main concept you need to understand when it comes to the photochemical reactions and photochemistry. I hope it's fine for you. Let's move on to see like let's move more depth into this, right? This is more interesting when it comes to more and more factors involved. So let me take you back again to here. So this is the ground state. Okay, this is the ground state. So this is the excited state. Now here we have the excited state. So you know there are two types of excited state, right? Singlet excited state and triplet excited state. This is the singlet. So we can denote it as S1. This is the S0. Okay. Singlet excited state, singlet ground state. And there is also our second type of excited state, which is the triplet excited state. This is the triplet excited state. Okay, triplet excited state. Look at the energy difference. So I have drawn this according to its energy difference, right? So this is the energy. So you can see the singlet excited state has relatively like high energy, right, than the triplet excited state. So like this can be changed, right? This is not exact. This can be changed based on the chromophore. Now what's the chromophore? Chromophore is a part in the molecule which where this excitation happens, right? So let's say a benzene. For a benzene, you know there are 5 electron clouds, right? There are 5 electrons. These 5 electrons can undergo excitation. Let's say aldehyde. In aldehyde, there is this lone electron pairs on oxygen, on heteroatoms. These can undergo excitation. Likewise, this chromophore. This is the chromophore here. This pi electron cloud. That's the chromophore in here. So based on this chromophore, these energy differences can be changed. Right? These energy differences can be changed. You need to understand that. We will talk more about each of type. Right? We will talk about the benzene types and we will talk about the aldehyde, ketones. So at that. When it comes to that, you will fully understand how this chromophore and excitation works for each individual. For now, let's take a situation like this, where we have a single state like this and triplet state like the energy like this. Okay. Now, when the excitations happen, okay, you know the direct excitation from ground state to triplet excited state is forbidden, so it won't occur. Now, what happens is ground state to singlet excited state. This is allowed, right? This is allowed. And after molecules has excited into this singlet excited state, they can undergo a process called intersystem crossing. Intersystem crossing. This is the main process where this triplet excited state get populated, right? It's not from the direct transition. It's from this S1 excited state, and to intersystem crossing, we have this triplet excited state get populated. Okay, these things you need to have the idea, right? So if your question asks like why this direct transition won't occur, you need to be able to give the right answer. So there should be that selection rule. You need to mention that in your answer. Those are the points where you can obtain marks, right? So I hope it's fine. Okay. Now another thing is, most question may ask you about this is like, why this photochemistry? Why this photochemical irradiation? Why this photochemical excitations other than the thermal excitation or irradiation? Irradiation means the excitation. Okay, what's the difference between these two? Photochemical irradiation and thermal irradiation. Now the thing is, in thermal irradiation, what we are going to do is we are going to apply heat. Okay, we are going to apply heat. So this heat is not a specific wavelength. Okay, heat is not a specific wavelength. So, but you know, when an excitation to happen, when a transition from ground state to this singlet excited state to happen, we need a photon exactly to this energy difference. Okay, we need a photon exactly to this energy difference. So this photon has a specific wavelength, sorry, CO lambda. Okay, this specific wavelength is there. So your energy contribution should be specific to this lambda value. But when it comes to thermal irradiation, okay, we don't have this specific wavelength. We have a wide range of wavelength of energies. So if you supply like let's say 1000 joules from your thermal irradiation, only 1 joule will be available for the excitation, because only 1 joule would be satisfy this lambda value expectation. But when it comes to photochemical irradiation, okay, when it comes to photochemical irradiation, we have this specific wavelength. Our providing energies wavelength is much more narrowed. So if you have supplied 100 joules, this is just hypothetical, right? These values, these are hypothetical values. So if you supply 1000 joules from photochemical irradiation, like let's say 700 joules would be acceptable for the irradiation. So it's more efficient than thermal irradiation, right? Thermal irradiation is much more wasting for most cases, right? There are some cases which is thermal irradiation is much more efficient, but in these cases, in this particular case, thermal irradiation is not more efficient, but the photochemical irradiation is much more efficient based on the energy supply. So this is the main difference between the photochemical irradiation and thermal irradiation. I hope you get the basic idea of this photochemistry, right? So in next video, let's talk about the more processes involving this photochemical irradiation, like quenching, fluorescence, these type of things which are more interesting. And if you have any problems, if you have any questions based on this, please feel free to comment below. I will try my best to give you the answers, right? And if you have anything to add for this content, please be free to apply follow below. So let's move on to our next video, which we will talk about more interesting thing about this photochemistry. Thank you.